Welcome to our deep dive today. We're going to be tackling a topic that I think is really interesting. It kind of sits at that intersection of like the tech world and the business world. We're going to be talking about this big push for what they call memory-safe programming languages. And this is all happening, of course, in a world that is increasingly concerned with software security, you know.
Yeah, and it's really interesting to see how this is all kind of playing out. Like we're moving away from this idea that security is just a tech problem, right? And more towards recognizing it as a real business risk. But we're at the point now where you've got senior executives, people who, let's be honest, probably don't know a whole lot about coding, being held accountable for the code that their companies are putting out.
Yeah, that's a huge shift, right? I mean, imagine having to explain to a board of directors why your software is vulnerable because of something called a dangling pointer. I mean, most of those folks probably only encounter that term doing a crossword puzzle. But before we get too far ahead of ourselves here, let's back up a bit. Could you give us a quick rundown on what exactly memory-safe languages are and why everybody's suddenly so focused on them these days?
Yeah, so at their core, memory-safe languages are designed to stop a whole class of security weaknesses that come up from how a programming language actually handles computer memory. See, the problem is, even really, really experienced developers, they can accidentally create these vulnerabilities. And of course, hackers are always looking for these things, right? They can exploit them to get their hands on sensitive information or even completely disrupt how systems work.
So it's not even just about, like, writing clean, elegant code, right? It's about the very foundation that the code is built on.
Exactly. Think of it like a house, right? If you build a house on a shaky foundation, it doesn't matter how nice the house is, how well built it is, it's always going to be at risk.
Makes sense.
A classic example of this is something called a buffer overflow. So this is where basically the program is trying to shove more data into a memory block than it can actually handle, right? And when this happens, it can overwrite the memory next to it, and that can corrupt data, or in a worst case scenario, it can even let malicious code get executed.
And that just sounds like a recipe for disaster, especially with, like, how interconnected all of our software is these days, right?
That's exactly right. I mean, interconnectedness, in a lot of ways, it means increased vulnerability, right? As these systems get more complex, more reliant on each other, the potential impact of even a small weakness, it just grows exponentially. And that is where this appeal of these memory-safe languages comes in, right? They're trying to head off these risks right from the get-go, trying to provide a more secure foundation to build software on.
So they're like the first line of defense, like trying to stop these memory mishaps before they even happen.
You could put it that way. But, and this is where it gets interesting as we kind of do this deep dive, there's this whole list of languages out there that are officially categorized as safe, right? We're talking big names, C#, Go, Java, Python, Rust, Swift, all the big players. But here's the thing. None of them are actually totally immune to vulnerabilities by default.
Wait, really? So you're saying a programming language can be labeled as safe and still have security loopholes. How does that even work?
It all comes down to this idea of unsafe code. And there's this term for it. It's called unsafe impedance. So even with all these safety features built in, these languages, a lot of times they still let you write unsafe code, which is basically code where those safety nets, they're just completely bypassed, sometimes on purpose, sometimes not.
So even when you're working within these languages, these safeguards, there's still a chance you can wander into the danger zone, so to speak.
Exactly. And unsafe impedance, it's basically a measure of how hard it is for a language to let someone write or include that unsafe code. The harder it is to do that, the higher the impedance, the more secure the environment usually is.
Okay, so it's like putting up roadblocks, right?
Yeah.
Making developers really think twice about whether they really need to take that risk, whether they need to potentially expose the whole code base to vulnerabilities.
That's a good way to think about it. And each language, it kind of has its own approach to this whole unsafe impedance thing. Maybe we can dive into some specific examples from the research. It might be helpful to see how this actually works in practice. I want to start with C#.
Let's take a look at C# and how it tries to walk that tightrope between safety and, still giving developers the flexibility they need.
So in C#, there's this method called it's called marshal.alloghglobal. It's a mouthful. Basically what it does is it lets you create, it's essentially an unsafe array. The problem is it doesn't actually overwrite any of the existing data in that spot in memory. So whatever information was there from before, it might still be hanging around. And that can lead to vulnerabilities.
So it's like you think you've got a clean slate, but there might be like remnants of something else lurking beneath the surface.
Right, and the tricky part is there's not really any big red flags in the code itself that are like screaming, hey, you've wandered into the unsafe zone. It takes experience, a keen eye to spot those potential risks.
That's such a subtle point, but it's so important. Even in these languages that are designed with safety in mind, if you don't have that visibility, you can easily end up with vulnerabilities you didn't even intend to create.
Exactly. And what's interesting is we see a really similar pattern when we look at Go.
So let me get this straight. Even in Go, which like it has this whole reputation for being, efficient, simple to use, even there you're saying there are these like hidden corners where you can stumble into unsafe code.
Yeah, that's right. In Go, you can actually create what are called unsafe pointers, but the thing is, they're not always explicitly marked as unsafe in the code itself.
Wait, really? So how do you even know if you're looking at one of these like ticking time bomb pointers?
Well, there is an option to use this package name unsafe, which kind of gives you a visual cue, but the problem is it's not mandatory. So you could be looking at code and it looks perfectly innocent, but under the hood, it's using these unsafe pointers.
Oh, so a developer could be introducing a vulnerability without even like realizing the potential consequences of what they're writing.
Exactly. And again, it really highlights how important it is to have, really thorough code review processes in place and people who really, really understand the ins and outs of the language they're working with, even when it's a language that's generally considered safe.
It almost seems like the burden of security awareness really falls on the developers themselves. It's a lot of responsibility.
Yeah.
What about Java, though? I mean, Java's been around forever. It's known for being really portable and having these huge libraries. Surely they've got, like, rock-solid safety measures in place, right?
Well, Java's a bit of an interesting case. It is designed with security in mind, but it relies on this thing called the Java Native Interface, or JNI for short.
Okay, and what does that do?
So basically, the JNI, it lets Java talk to libraries that are written in other languages, like C. And this is really powerful because it gives you a lot of flexibility. But as you might imagine, it also opens the door for potentially unsafe code to sneak in.
So it's like you build this amazing fortress, right? But you leave one little drawbridge that can be lowered at any time, and suddenly the enemy's inside the walls.
That's a great analogy. Java's tried to address this. Like they've introduced things like the foreign function and memory API. These are supposed to make those external interactions more secure. But at the end of the day, it's still this balancing act. Do you prioritize safety or do you prioritize being able to easily integrate with all these other things?
Right, right. I guess you could never fully escape those trade-offs.
Yeah.
So we've talked about C#, Go, Java. Now, what about Python? Because Python's got this reputation for being really beginner-friendly, right?
Right.
So you would think that would also mean it's inherently safer to use.
That's a common assumption. And to be fair, when you're using Python in isolation, like you're not pulling in a bunch of external stuff, it can be pretty secure. But its strength, which is that it's super easy to integrate with all these external libraries, that's also kind of its downfall when it comes to security. Because a lot of these libraries are actually written in languages like C.
Ah, so you end up with this, like, potentially risky code hiding behind this facade of simplicity.
Yeah, exactly. And this is a really big deal in the machine learning world, right? Python is huge for machine learning. But a lot of those libraries, they depend on these external components, which means you could have vulnerabilities baked in and the developers might not even know it.
That is kind of mind-blowing, right? That
hmm
this seemingly harmless machine learning algorithm could actually be a security risk because of how the underlying code is structured.
It's definitely something to be aware of. And it just goes to show that, you really need to understand the whole ecosystem your code is operating in, not just the language itself.
So again, vigilance, awareness, those are key.
hmm
Okay, so we're on a bit of a roll here. What about Rust? Rust has gotten pretty popular lately, and a lot of people are saying it's like super safety conscious. Does it manage to avoid these kinds of issues?
Rust is definitely a step in the right direction when it comes to memory safety. They've tried to address this whole unsafe code issue head on. So in Rust, if you're working with anything that could potentially be unsafe, you have to mark it with the keyword unsafe.
So at least there's like a big flashing warning sign for developers, right? Like, hey, be careful here. This stuff could be dangerous.
Yeah, but even with that, it's not foolproof. You see, Rust tries to encapsulate these unsafe blocks of code, make them easier to manage, but it's still possible to wrap those unsafe blocks inside functions that from the outside look perfectly safe.
Oh, so it's like putting a warning sign on a box, but then hiding that box inside of another box.
Exactly. And like some of the other languages we've talked about, REST still lets you bring in external libraries. So again, that's always a potential point of vulnerability if those libraries aren't, super carefully checked.
It seems like every language has its quirks. So to wrap up our little tour here, what about Swift? How does it handle this whole safety versus flexibility thing?
Swift actually takes a similar approach to REST. So when you're working with pointers, which are often a source of memory problems, you have to use this unsafe keyword. And that's good, right? That transparency is helpful. But again, it's not a magic solution. Swift also lets you use C libraries, which means those vulnerabilities can still sneak in through those external dependencies.
So the more we dig into this, it feels like there's this recurring theme, right? Like no matter how well designed a language is, you can never completely eliminate the possibility of vulnerabilities, especially when you start factoring in all these external elements. So is it even possible to create a truly secure coding environment? Or are we like chasing an impossible dream?
That's the million-dollar question, isn't it? And honestly, it's not about finding this perfect language, this silver bullet that magically makes everything secure. It's more about understanding the limitations,
Yeah,
embracing good practices, and fundamentally shifting our whole mindset to put security first.
I like that.
And there's actually, our research talks about these two languages, Erlang and Elixir. They kind of offer a different perspective on this whole challenge. Have you heard of those?
Erlang and Elixir. Yeah, I've heard the names. I don't think they're quite as mainstream, at least not yet. But what makes them stand out in terms of security?
Well, for starters, they run on this virtual machine called Beam. And Beam is designed from the ground up to be really resistant to a lot of these memory vulnerabilities we've been talking about. And on top of that, Erlang and Elixir, they're what we call functional and declarative languages. And what that means is they're structured in a way that makes it a lot less likely for developers to make the kinds of errors that often lead to these vulnerabilities.
So it's like they've created an environment where, like, the rules of the game discourage those bad coding habits that can lead to security holes.
That's a great way to put it. So Erlang and Elixir, when you use them properly, they're generally considered secure by default, precisely because they kind of inherently limit how much you can even mess around with memory, which is something that languages like C or even Rust, they allow. But, and this is a big but, even they aren't totally immune to the possibility of having unsafe code.
Of course, there's always a catch, right? So what's the loophole with Erlang and Elixir?
It comes in the form of something called native implemented functions, NIFs for short.
Ifs. Okay, so that sounds pretty harmless. What's the downside?
Well, basically, NIFs let you take code that's written in languages like C and plug it right into your Erlang or Elixir programs. And that can be really handy sometimes, don't get me wrong, but it also means that we're right back to those same old vulnerabilities potentially sneaking in.
So even with all their security features, Erlang and Elixir, they can't totally escape the risks that come with using external code.
You got it. But this is where that idea of unsafe impedance that we talked about earlier, it becomes really crucial. You see, Erlang and Elixir, they're so focused on security from the ground up that just the process of making a NIF, of integrating it, it's way more involved than, say, just dropping a few lines of C code into a Python program.
So it's not just about whether you can use unsafe code, it's about how much effort you have to go through to do it.
Yeah.
The harder it is, the less likely people are going to cut corners.
Right, exactly. And the hope is that by making it more difficult, maybe even a little bit painful, to bring in those potentially risky elements, Erlang and Elixir kind of nudge developers towards finding safer ways to do things.
They're encouraging good habits right from the start.
Yeah, it's about shifting that default, right? Making security the path of least resistance, not just an afterthought.
That makes a lot of sense. So if even these languages with all their security features still have this potential weak point, I mean, what's the answer? Are we ever going to be able to write truly secure code, or is that just like a fantasy?
Well, like we were saying before, it's not really about finding that one perfect language, the one that solves everything. It's more about having the right mindset. It's about constantly trying to improve how we do things, being aware of the limitations, and always, always putting security front and center. And actually, our research, it talks about this really cool concept called the Unsafe Acceptance Process, or UAP.
Unsafe acceptance process. That sounds like we're just like giving up and saying, okay, unsafe code is inevitable. Let's just accept it.
No, not at all. Think of it more like we're setting the bar incredibly high for even considering the use of unsafe code, let alone actually allowing it.
Okay.
The whole point of a UAP is to crank up that unsafe impedance that we've been talking about, make it a last resort, not something you just do because it's easier or faster.
So no more just casually dropping in some C code because it's convenient.
Ideally, no. A really strong UAP, the way they describe it in the research, it has several key parts. First, you've got to have what they call a proof of necessity. That means developers actually have to demonstrate, like without a shadow of a doubt, that there is absolutely no other way to achieve what they need to do without resorting to unsafe code.
No more like, well, this is just easier excuses.
Exactly. And then you've got to do a full-on security risk assessment. Like really analyze what could go wrong, what vulnerabilities might pop up if you introduce this unsafe code.
So shining a spotlight on all the potential downsides, right? Making sure everyone understands the risks involved.
Yeah, exactly. And it doesn't even stop there. You've got rigorous code reviews, performance testing to make sure it's not going to slow the whole system down. And then get this, even after all that, you still have to actively look for alternative solutions, safer ways to do it, even if those solutions are less elegant or maybe a little bit less efficient.
Wow, so this UAP is like this multi-layered process designed to make you really think multiple times before you even think about using unsafe code.
That's the idea. It's about building a culture where security is just baked into every step of how you develop software, not something you tack on at the end.
I love that. This has been a really, really insightful deep dive, to say the least. We've gone deep into the world of memory-safe languages, and I think we've uncovered a lot of interesting stuff along the way.
Yeah, it's been fun.
We've seen that even languages designed for safety can still have vulnerabilities, especially when you factor in things like external libraries and dependencies. And we've also learned about some really important concepts like unsafe impedance and this unsafe acceptance process, both of which highlight how crucial it is to be aware of the risks, to have solid processes in place, and to always, always prioritize security in everything we do.
Yeah, absolutely. And I think the biggest takeaway from all of this is that there's no magic solution, right? There's no one language, no single tool that's going to eliminate all risk. It takes a multifaceted approach, and it takes a real commitment to understanding the tools we're using and how to use them safely.
Well said. And as software becomes more and more central to, well, everything, these conversations, these deep dives into the complexities of security and reliability, they're only going to become even more important.
Absolutely.
It's a shared responsibility, from the executives making the big decisions down to the developers writing the code and everyone in between.
Couldn't agree more.
Well, that's all the time we have for today's deep dive. Thank you so much for joining us. Until next time, stay curious, stay safe, and may your code be ever secure.